In this video, we're going to get some practice with partial fraction decomposition. We'll go through each of the common cases found in a Calculus 2 class. The first situation is when you're integrating a rational function where the degree of the numerator is greater than or equal to the degree of the denominator, as we see in number 1. The integral of x squared divided by x plus 1. We're going to rewrite that rational expression using long division. So we're going to integrate x minus 1 plus 1 over x plus 1 dx. Now, before we integrate this, there's another way we could have done this that was maybe a little more efficient. And that is taking our numerator, x squared, and noticing that we can subtract 1 and add 1 to it. Then we can split up the integrand into two separate rational expressions, x squared minus 1 over x plus 1, plus 1 over x plus 1, like that. The first numerator is a difference of squares. We cancel, and we've got x minus 1 plus 1 over x plus 1, just as we saw above when we did long division. Integrating this, of course, is pretty straightforward. 1/2 x squared minus x plus the ln of absolute x plus 1 plus c. Go ahead and pause the video, do number 2. Number 3, we're integrating x minus 9 over x squared plus 3x minus 10. Here, you'll notice that the denominator factors. And in the denominator now, we have two linear factors, x plus 5 and x minus 2, and neither of them is repeated. When this happens, to decompose our rational expression, we're going to use what we often refer to as case 1, where we're going to separate the rational expression as the sum of two rational expressions where we're going to have different constants in the numerator. Let's see how this works. So x minus 9 over x plus 5 times x minus 2, we're going to rewrite as capital A, x plus 5 plus capital B over x minus 2. And our goal is to find A and B, so we have these two separate rational expressions, and then we can integrate from there. So if we were to make a common denominator, we would have to take A and multiply by x minus 2, and we would have to take B and multiply by x plus 5. Now, if we did that, in the denominator of each, we would have x plus 5 times x minus 2, like this. Notice if you cancel the x minus 2's here, you're back to the previous A over x plus 5, and if you cancel the x plus 5's here, you're back to the B over x minus 2. And our goal is to find A and B so that that sum is equal to x minus 9 in the numerator, x plus 5 times x minus 2 in the denominator. Now, really, all we care about to make these two sides of our equation equal to each other is to set the numerators equal to each other, because the denominators are always the same. So to save us a little bit of writing here, I'm just going to go ahead and erase all this. Now we're going to take the A and distribute it. So you have ax minus 2a, same thing with the b, bx plus 5b, and that's all going to equal x minus 9. We're going to take these two terms, right, ax plus bx, and I'm going to factor out an x, like this. Then I'm going to take the two constant terms and just put them in back, like this. Now, remembering that this expression has to equal x minus 9, that means that the constant part of this expression, right, there's no x involved here, has to equal -9. And the coefficient in front of x here has to equal the coefficient in front of x here, which is really just a 1. So that means that a plus b in green has to equal 1, and -2a plus 5b has to equal -9. Now we have two equations, two unknowns. We can solve this using substitution method or elimination method. I'll usually do elimination method because it feels to me a little more efficient. So I'm going to take a plus b equals 1 and multiply everything by 2. And then I'm going to combine it with the second equation, -2a plus 5b equals -9. And when we add straight down, we get 7b is equal to -7. So b has to equal -1. Now, if we take b and plug it back into a plus b equals 1, we're going to get a minus 1 equals 1. Now we add 1 to both sides and we get a equals 2. So this means that we can take our integral from above, this one here, and rewrite it with an integrand that looks like this. In other words, we have a is 2 over x plus 5, and b is -1 over x minus 2. At this point, you can pause the video, you can multiply to get common denominators, and then combine, and it should take you back to the original integrand. Continuing on, the integration now is relatively straightforward. We have the integral of 1 over x plus 5 dx times 2 minus the integral of 1 over x minus 2 dx. We have 2 ln of absolute x plus 5 minus ln of x minus 2 plus c, and we're done. Go ahead and pause the video, do number 4. You're going to follow pretty much the same steps as we did in number 3. Number 5, the integral from 1 to 2 of 4y squared minus 7y minus 12 all over y to the third minus y squared minus 6y dy. So first we're going to factor the denominator. And we notice that the factored form of the denominator has 3 factors. Each of them is a linear and none of them are repeated. So this is going to be case 1 like we saw in the previous couple of problems. So we're going to rewrite this rational expression like this. Now, if we were to add these 3 rational expressions, we would need common denominators. And to do so, we would have to take a and multiply it by y plus 2, y minus 3, and b would have to be multiplied by y and y minus 3, and c would have to be multiplied by y and y plus 2. Again, as we saw earlier, this would give us the same denominator in each one if we were to write it all out like this. And if we were to add these together, we would get 4y squared minus 7y minus 12 in the numerator, and in the denominator, we would have this again. Just as we saw before, in order for these two sides to be equal, the numerators would have to be equal. So it's easier if we just get rid of all of the denominators. Now we'll multiply on the right-hand side. Now we'll group our terms together so that we have all of our y squareds. In other words, this term, and this term together would look like this. Then we'll group all of our terms with y. That's this one, and this one. And finally, we're left with this for our constant term. Now, in order for the right-hand side to equal the left-hand side, negative 6a, the constant term, would have to equal negative 12. And negative a minus 3b plus 2c would have to equal negative 7. And finally, a plus b plus c would have to equal 4. So we'll set up those three equations. So we have three equations and three unknowns. We should be able to solve this by elimination or substitution. Immediately, we see that a is equal to 2 by dividing both sides by negative 6. And now I can rewrite these two equations. If I put in a 2 in for a, and here I have negative 2 minus 3b plus 2c equals negative 7. These will become b plus c is equal to 2. And here we have negative 3b plus 2c is equal to negative 5. If we take this equation and multiply by 3, we get this. And now we add these straight down. The b's cancel. We have 5c is equal to 1. So c equals 1 over 5. We can now substitute 1 over 5 into b plus c equals 2. So we have that b is equal to 9 over 5. Now that we have a, b, and c, we can plug those values into here and rewrite our integral like this. And now we're ready to integrate. We have 2 ln absolute y plus 9 over 5 ln of absolute y plus 2 plus 1 over 5 ln of y minus 3, and all of this is being evaluated from 1 to 2. Plugging in 2, we have ln absolute 2, which is really just ln 2, plus 9 over 5, again plugging in 2, we'll have ln 4 here, plus 1/5. We have ln of negative 1 in there, but then the absolute value makes that 1. And of course, the ln of 1 is 0, so this guy is going to 0 out. Minus, plugging in 1 now, we have 2 ln 1, which again will 0 out, plus 9 over 5 ln 3, plugging into the second term, plus 1 over 5 ln of negative 2, but absolute values will make that just a 2. Again, this guy zeroes out, this guy zeroes out, so we're down to 2 ln 2 plus 9 over 5 ln 4 minus 9 over 5 ln 3 minus, not forgetting to distribute the negative above, 1 over 5 ln 2. Now, we're in pretty good shape here. We might notice that we have an ln2 here, an ln2 here, and we can rewrite this as an ln2. In other words, we know that the 4 here is really 2 squared. So I'm going to go ahead and erase that and put a 2 squared. And then we can bring this 2 down in front. So we're going to end up with 2 ln 2 plus 18 over 5 ln 2 minus 9 over 5 ln 3 minus 1 over 5 ln 2. Now we'll combine the terms involving ln 2. Let's change this to a 10 over 5. These two combined to a 28 over 5 minus this one will give us a 27 over 5. So we have 27 over 5 ln 2 minus 9 over 5 ln 3. We could potentially rewrite this in another way, but we'll just leave it at that. Go ahead and pause the video and do number 6, following the same steps as we just went through in number 5. Number 7, the integral of 1 over the quantity x plus 5 squared times x minus 1 dx. In this case, our denominator has linear factors again, but you'll notice that we have x plus 5 squared. We call that a repeated linear factor. And when that happens, we're going to go to what's often referred to as case number 2, where our repeated linear factors are going to get multiple terms when we do our partial fraction decomposition. The first term has the linear factor to the first power, the next term has it to the second power, and we would continue on like this until we reach the power of that repeated linear factor. In this case, the x plus 5 is raised to the second power, so we're only going to need to repeat it twice. In other words, we're going to take our original rational expression and rewrite it as a over x plus 5 plus b over x plus 5 quantity squared plus c over x minus 1. Now, if we were to combine these, we would make common denominators just as we did before. So a would get multiplied by x plus 5 and x minus 1. B would get multiplied by just x minus 1 because we already have an x plus 5 quantity squared in the denominator. And C would get multiplied by x plus 5 quantity squared. Again, we won't write the denominators here, but we realize that in order for the two sides to be equal, this numerator here has to equal 1. Now we'll multiply and distribute each of our constants, a, b, and c. Now we'll group together our x squareds. So we have ax squared here, and we have cx squared there. That'll give us a plus c x squared in yellow. Now we have a 4ax, a bx, and a 10cx. In purple. And finally, we have our constants in blue. So just as we saw before, this expression here has to equal 1. Well, 1 is a constant, so this will equal 1. If you notice here, we don't have any x's or x squareds, so that means that this coefficient has to equal 0 and this coefficient has to equal 0. And we end up with these three equations. Noticing that if we add these two together, the b's will cancel. And we get negative a plus 35c equals 1. And taking our first equation, a plus c equals 0, and adding straight down there, we'll get 36c is equal to 1, leaving us with c equals 1 over 36. Plugging back into a plus c equals 0, we get that a is equal to negative 1 over 36. And then finally, plugging into this equation here, we have 4 times negative 36, which will give us that, plus b, which we're looking for, plus 10 times c, which will be 10 over 36 equals 0. That will give us b plus 6 over 36 equals 0, so b equals negative 1 over 6. Now we're going to plug in our a, b, and c into this expression and rewrite our integral. Now we'll go ahead and rewrite this and integrate. We could split it up into 3 integrals like this, putting the constants on the outside. First integral is negative 1 over 36 ln of x plus 5. For this next integral, we could do a u substitution, or we can try to reverse engineer it. If we think about x plus 5, and we want a negative 2 here after we take a derivative, we probably want to start with a negative 1. If we multiply that down in front and subtract 1 from the exponent, we should be in pretty good shape as long as we put a 1 over 6 in front. You can pause the video and check that. So we end up with plus 1 over 6 times x plus 5. And finally, we have 1 over 36 ln of absolute x minus 1 plus c. Go ahead and do number 8, following the same steps. Number 9, the integral of 5x squared plus 3x minus 2 all over x to the third plus 2x squared dx. First, we'll factor the denominator. Again, we have a repeated linear factor in the denominator with that x squared. So our partial fraction decomposition will look like this. So our numerator is going to equal a times x plus 2 plus b times x plus 2 plus c times x squared. Multiplying, we have ax squared plus 2ax plus bx plus 2b plus cx squared. Now we'll group our x squareds to get a plus c times x squared plus 2a plus b times x plus 2b. Now, equating these coefficients, we're going to see that a plus c is equal to 5, 2a plus b is equal to positive 3, and 2b is equal to negative 2, giving us these three equations. These three equations would solve like this. So we have a is 2, b is negative 1, and c is 3. There's another way we could have done this. That's maybe a little more efficient in this case. If we go back to here and let x equal 0, well, over here, we're going to end up with 5 times 0 squared plus 3 times 0 minus 2, which would give us a negative 2, like that. And over here, this factor would 0 out, and that factor would 0 out. So we would just have b times 0 plus 2, because again, we're plugging in 0 for our x's. Again, we just have this one term, and that's what I have there. And when we solve this, we get negative 2 is equal to 2b, so b is equal to negative 1, which is exactly what we got with the other method. From there, if we let x equal negative 2, on this side, we're going to have 5 times 4, because we're squaring the negative 2, so that's 20, minus 3 times negative 2, which is a negative 6. So 20 minus 6 minus the negative 2 is going to give us 12 equals. And then on this side, plugging in negative 2, this factor would go to 0 because negative 2 plus 2 is 0. Same thing with this factor. And if we plug in negative 2 here, we would have negative 2 squared, which is 4 times c. And then dividing, c equals 3. And finally, once we have c, we can find a by plugging in here. And we get that a equals 2. If you prefer the shortcut, that's fine, but it's not going to work every single time. It will work when we have linear factors. But as we'll see in the problems to come, this technique won't work when we have factors in the denominator that are irreducible quadratics. So now we're going to take our a, b, and c, plug them into here, and rewrite our integral. So we have the integral of 2 over x plus our b is -1 over x squared plus our c is 3 over x plus 2. And now we're ready to integrate. We're going to get 2 ln absolute x plus 1 over x. Pause the video and check that that's been integrated correctly, plus 3 ln of absolute x plus 2 plus c. Pause the video, do number 10 in much the same way. Number 11, the integral of 3x squared minus 4x plus 5 all over the quantity x minus 1 times the quantity x squared plus 1. You'll first notice that the denominator is factored as far as we can go. We cannot factor x squared plus 1. That's what we call an irreducible quadratic. When this happens, we go to case 3. When we have an irreducible quadratic in the denominator, our partial fraction decomposition will require us to put an ax plus b in the numerator. Let's see how this works. Our first factor in the denominator is linear, so we can write a over x minus 1. Our second factor is irreducible quadratic, meaning it does not factor, and we're going to write bx plus c like that. Now we're going to proceed just as we have in the past. We're going to take the numerator here, and we're going to multiply a by x squared plus 1. And then we're going to multiply the bx plus c numerator by x minus 1. Grouping the ax squared and the bx squared. Now grouping our terms with x's. And finally, grouping our constants. So in order for the two sides of this equation to be equal, we'll need a plus b to equal 3. We'll need negative b plus c to equal -4. And we'll need a minus c to equal +5. And we get these three equations. Solving these by elimination, if we add these two, we're going to get a minus b is equal to 1. And then taking the first equation, a plus b is equal to 3, and adding straight down, we get 2a is equal to 4, so a is equal to 2. Plugging back into either of the equations above, we see that b has to equal 1. And then plugging back into one of the original equations involving c, we notice that c has to equal -3. Now we're ready to rewrite our integrand by plugging in a, b, and c into here. So our integral becomes a over x minus 1, which is 2 over x minus 1, plus b, which is 1, x, plus c, which is -3, over x squared plus 1, like that. We can rewrite this as 3 integrals. With the first integral, we have 2 ln absolute x minus 1. With the second integral, we could do a u sub. I think we'll find we'll get 1/2 ln absolute of x squared plus 1. You can pause the video and check that for yourself. And finally, with the last one, we notice we have 1 over x squared plus 1 after we factor out the 3, and that's a tan inverse of x, like this. We could rewrite the first two terms using properties of logs this way. When we square that quantity, x minus 1, it will be positive, so we don't need the absolute values. And the same thing when we bring the 1/2 exponent up, so we have the square root of x squared plus 1. Pause the video, follow the same steps on number 12. Number 13, the integral of 1 minus y plus 2y squared minus y to the third all over y times quantity y squared plus 1 squared dy. Here in the denominator, we have the linear factor y, but then we have the repeated quadratic y squared plus 1 quantity squared. And here we have case 4, where we have repeated irreducible quadratic factors in the denominator. So this here is our irreducible quadratic, and then it's being raised to the second power, like this. In the numerators, you notice we have a linear ax plus b. So now our partial fraction decomposition will be a over y, our linear factor, plus by plus c over y squared plus 1, our irreducible quadratic, plus dy plus e over our irreducible quadratic squared. And now we continue just as we have in all the other problems, equating the numerators. We'll group our y to the fourth terms. We have 1 y to the third term. Now collecting our squared terms. Then our linear terms, y to the first power. And finally, we have a constant a in back. So comparing coefficients, we notice that there is no y to the fourth term. So a plus b is equal to 0. Looking at our y to the third term, we have that c has to equal -1. We have 2a plus b plus d on the squared term has to equal 2. C plus e on the linear term has to equal -1. And finally, a has to equal 1 for the constant term. If a is 1 and we plug that in here, we see that b is -1. We have that c is -1, and if we plug that in here, we see that e is 0. We can plug a and b into this equation to find d to get 2 times 1, which is 2. b is a -1 plus d is equal to 2. That means we have 1 plus d is equal to 2, meaning that d equals 1. Now we'll plug each of these values into here to rewrite our integral. And so now our integral looks like this. Now we can split this into 4 separate integrals. We have the integral of 1 over y dy minus the integral of y over y squared plus 1 dy minus the integral of 1 over y squared plus 1 dy. And then finally, the integral of y over y squared plus 1 quantity squared dy. Our first integral will be ln of absolute y minus, here we could do a u substitution. We would get something like this. You can pause the video and double check that. Next, we'll have a tan inverse of y. And lastly, again, we could do a u sub and we get something that looks like this. Go ahead and do number 14, following the same steps.